Welcome to the Bodhi Academy. My name is Amisha Klaso, and in today's video we'll continue with our class 11 chapter 6 equilibrium. So in today's video we will learn about the law of chemical equilibrium and the equilibrium constant. So a mixture of reactants and products in the equilibrium state is called an equilibrium mixture. Okay, so whenever we have a mixture of both reactants and products which are both at equilibrium, that mixture itself is called as the equilibrium mixture. Now in this section we will address a number of important questions about the composition of equilibrium mixtures. What is the relation between the concentration of reactants and products in an equilibrium mixture? How can we determine equilibrium concentrations from initial concentrations? What factors can be exploited to alter the composition of an equilibrium mixture? So the last question in particular is important when choosing conditions for synthesis of industrial chemicals such as hydrogen, ammonium, calcium oxide, etc. So now if we are carrying out any reaction, especially the reactions which are carried out on large scales in the industries, there we need to ask this very important question, that what are the factors that will that can be exploited to alter the composition of an equilibrium mixture. Okay, so now here, to answer these questions, we have to look at a general reversible reaction. Say we have reactants A and B which give us products C and D. Now where A and B are the reactants, C and D are the products in the balanced chemical reaction. Okay. Now on the basis of experimental studies of many reversible reactions, the Norwegian chemist Cato, Maximilian Goldberg and Peter Weige proposed in 1864 that the concentration in an equilibrium mixture are related by the following equilibrium equation. So these two chemists, they came up saying that the equilibrium mixture is related by a equilibrium equation that says Kc equals to Cd upon AB. Now this boxed brackets over here indicate that we are talking about the concentration of C and concentration of D. So here we are basically taking a ratio of the product of concentrations of the products upon the concentration of the products of concentration of the reactants. So where this Kc which is here, it is known as the equilibrium constant. In the expression on the right side, this expression is called as the equilibrium constant expression. The equilibrium equation is also known as the law of mass action. Okay, because in early days of chemistry, concentration was called as active mass. So initially, now what we call concentration, it was initially known as active mass. So that is one of the reason that it is this equation, equilibrium equation, it is also known as the law of mass action. Now in order to appreciate their work better, let us consider reaction between gaseous H2 and I2 carried out in a sealed vessel at 731 Kelvin. So now to understand this, we are taking an example wherein we are carrying out a reaction of hydrogen and iodine in a sealed vessel at a temperature of 731 Kelvin. Now here hydrogen gas we have taken of 1 mole. 1 mole of iodine gas we have taken, and the product is hydrogen iodide, that is 2 moles of hydrogen iodide, that is also gas. Now 6 sets of experiments with varying initial conditions were performed, starting with only gaseous H2 and I2 in a sealed reaction vessel in first 4 experiments, and only HI in the other 2 experiments. Now they carried out 6 sets of reaction. In first 4 reactions in the sealed vessel, they took H2 gas and H2 gas and iodine gas I2. In the other 2, that was 5 and 6, in that they took only hydrogen iodide. Now experiment 1, 2, 3 and 4 were performed taking different concentrations of H2 and or I2. So here in the first 4 vessels, they had varying concentrations of hydrogen and I2. And with time, it was observed that the intensity of the purple color remained constant and equilibrium was attained. So now we know that the purple color is due to the presence of iodine. So whatever fumes were going on, that color remained persisted, it remained constant, okay, it was not changing. So therefore when it was not changing, we were able to say that the equilibrium stage was attained. Similarly, for experiments 5 and 6, the equilibrium was attained from the opposite direction. Why? Because we have put the products first, okay. Now data obtained from all 6 sets of experiments are given in table 6.2. So here we have all the experiments. So 1, 2, 3, 4, these are the ones with H2 and I2 concentration, varying I2 concentration. 5 and 6, here we didn't take H2, I2, we directly took hydrogen iodide. And here are the respective equilibrium concentrations of each of them. Now it is evident from the experiments 1, 2, 3 and 4 that number of moles of dihydrogen reacted equals to number of moles of iodine reacted equals to half number of moles of HI formed. Okay, so here if we see that this is basically almost the half of this value, okay. So they are saying that this overall, we can say for the first 4 reactions which are given here, we can say that the moles of dihydrogen that have reacted, they are equal to the number of iodine moles that have also reacted, that equals to half the number of moles of HI that is being formed. So also from experiment 5 and 6 indicate that H2 is directly equivalent to concentration of H2 is equivalent to I2. Knowing the above facts, in order to establish a relation between concentration of the reactants and the products, several combinations can be tried. Let us consider the simple expression. So now before they derived the equilibrium constant, they tried various other combinations just so as to get the equilibrium constant. So one of them is this. So here they have taken HI upon H2 and I2, concentration of HI upon product of concentration of H2 and I2. Now it can be seen from table 6.3 that if we put the equilibrium concentration of the reactant and products, the above expression is far from constant. However, if we consider the expression concentration of HI raised to its stoichiometric value divided by same for the concentration of the reactants, in that case we were able to see that the values were remaining constant. So if we look here, see, this is the first one that we take. Here we didn't take any raised to power, those stoichiometric values were considered. So if you see here, the equilibrium constants were quite varying, okay, they were not even close to being constants. But if you take into consideration the stoichiometric values which are there, in that case we were able to see some constant pattern. So we find that this expression gives constant value in all 6 cases. It can be seen that in this expression, the power of the concentration of reactants and products are usually the stoichiometric coefficients in the equation for the chemical reaction. So now here we have raised this 2 because in the equation we had taken 2 moles, that is the stoichiometric value, whereas for H2 and I2 we had only 1 mole itself. Then thus for reaction H2I2 giving 2HI following equation 6.1, the equilibrium constant Kc is given as Kc equals to square of concentration of HI divided by concentration of H2 into concentration of I2. Generally the subscript that is there is omitted from the concentration terms. It is taken for granted that the concentrations in the expression for Kc are equilibrium values. We therefore write it as HI concentration of 2 upon that. The subscript C over here, this Kc having this subscript C, it tells us that the expression is expressed in terms of concentrations, that is mole liter inverse. So now at a given temperature, the product of the concentration of the reaction products raised to the respective stoichiometric coefficients in the balanced chemical equation divided by the product of the concentrations of the reactant raised to their individual stoichiometric coefficient has a constant value. This is known as the equilibrium law or the law of chemical equilibrium. Now this whole statement is basically that Kc equation in terms of words, okay. So that is known as the equilibrium law or the law of chemical equilibrium. So the equilibrium constant for a general reaction, say A giving B plus giving C plus TD. Now this can be expressed, the small a, b, c and d, they are the stoichiometric values. So you can express it in that terms, where A, B and C and D are the equilibrium concentrations of reactants and products. So if we have equilibrium constant for this reaction, ammonia plus oxygen giving nitrous oxide plus H2. So here this stoichiometric values will go as the raised to values. So molar concentration of different species is indicated by enclosing these in square brackets and mentioned above. It is implied that these are equilibrium concentrations. While writing expressions for equilibrium constant, symbol for phases, solid, liquid, gases are generally ignored. So in this case, we don't really consider the state of the matter that is there. So let us consider the equilibrium constant for reaction H2 plus I2 giving 2HI. So here we are saying this equals to X. So the equilibrium constant for reverse reaction. Now if this was from reactants going to products, so here now we are going from products to reactant, so the entire Kc will also reverse. So here what we can say that Kc will become the inverse of the given Kc value. This Kc value which we have got for this other reverse reaction, it will just be, the answer will be inverse of this Kc. So equilibrium constant for the reverse reaction is the inverse of the equilibrium constant for the reaction in the forward direction. So if we change the stoichiometric coefficients in a chemical equation by multiplying throughout by a factor, then we must make sure that the expression for equilibrium constant also reflects the change. So whatever changes are happening, whatever stoichiometry is changing, has to be reflected in the equilibrium equation, or else the values will go wrong. So for example, if we have half H2 and half I2 giving us HI, 1 mole. So in this, here also we also have to mention the power raised to as half, so as to get the correct value. So therefore here what we can say is that finally, depending on the chemical reactions, okay, this value of Kc will change, and we have to be very specific so as to what is the chemical reaction and what is the equilibrium constant. Okay, so that was it for today's video. I hope you have understood. Please don't forget to like, share and subscribe to the Bodhi Academy.